All right, so here we are, week 11, day 1, and basically there's two things as we work our way towards discussing nerve signal conduction. There's really two things we need to do. One, we need to figure out how resistors act in circuits, which we've been building towards for a few days. And then we need to see how capacitors work in circuits and just the basic rules about how they change current. These are kind of why we're spending so much time on these two ideas. And on Friday, we're going to be able to put it, hopefully by Friday, we'll be able to put it all together and discuss how nerves work. But for today, we're going to do just resistors and circuits and the basic idea of what an electrical circuit is and how it works. So the chapters for today's lecture are chapters 23.1 to 23.3. So we're going to talk about this first from just kind of like a physics engineering application perspective in terms of how we talk about circuits, how we draw them, so on and so forth. So if you're an electrical engineer, there's a few things that always appear again and again in circuits that are used for various different things. One are, of course, power sources like batteries. There are different types of power sources, but as far as we're concerned in this class, every power source is going to kind of be modeled as a battery in a sense. A battery being something that provides energy to a system to separate charge. We could also have wires that conduct current, things that limit current, which we're going to call resistors. A light bulb or something like that could be thought of as a resistor as well. However, sometimes we think about them as being their own thing. We could also have junctions of wires, capacitors in circuits, and ways to connect or break wires to allow current to flow or to completely stop it. And those are called switches. When we talk about circuits, one of the things that you may have seen if you worked in a lab or if you've ever built any electronic thing at some point in your life is that there's a specific type of symbols for all of these components that you put together to make a schematic diagram, meaning a simplified diagram that kind of shows what's going on in the circuit. So before we start, before we get into really the physics here, let's just look at some of these symbols. So first one for the battery, it's a symbol that looks like this. It's two wires going in, and then there's all these different horizontal lines. These kind of represent inside of a battery or a chemical battery. They're made of different stacked layers of different chemicals that are reacting with each other to produce the energy you need to separate charge. So that's kind of where this symbol comes from. The longer line, the longer horizontal line here, represents the positive side of the battery. Now that's something that's really hard to remember and it's hard to kind of see. So often in a lot of diagrams, you'll also see markings like this, marking what the positive and negative side of the battery is. For a wire is going to be anything that conducts current, at least theoretically, without resistance. So a wire is some really conductive metal that's resistance is approximately 0. So something like copper, even though its resistance isn't truly 0, it's a pretty good conductor. Those type of things are just drawn as straight lines in a circuit diagram. If we have something that is meant to limit current, something that has a non-trivial resistance, something that we can't ignore, where the resistance is somewhat higher, then we draw it like this. So it's a little kind of jagged, squiggly line meant to, I guess, kind of represent how electrons kind of bounce around and lose energy inside of a resistor. So this resistor here, usually in an actual circuit, there are these cylinders, usually of a material like tungsten, something that still conducts, but not as well as like copper or aluminum or gold. Light bulbs kind of have this little like curly thing inside a little bulb. We won't work with them much in our class, but just kind of showing you there. Junction of wire, where two wires meet, is more or less basically like you would expect. The only thing here is that regardless of how they meet, if they meet at a right angle or not, it's always kind of drawn at a right angle if possible. So you try to draw the junction in a way that simplifies what's going on. So these wires there might be like loop-de-loops here or something where this wire is like going off this way and this way. We try not to draw that in our diagrams. Instead, we try to keep things as simple as possible. So you always draw wire junctions at right angles and clean things up as much as possible. Let me just go back and get rid of that drawing that I did. So capacitor is again also what you would, I think what you would expect, two horizontal lines as opposed to the battery with the space between. So two plates that store charge. Capacitors are often used to store charge in circuits and then release it at a later time as like kind of a stored current. And a switch, again, I also think it's quite straightforward. So when we draw these, when we talk about and think about these different types of things in what we call an electrical circuit, meaning all these devices kind of connected by wires, allowing the current to make a complete loop from one end of the battery to the other, we're going to use these symbols. And just kind of as an example of what I was showing you before, regardless of how the different kinds of elements in a circuit are connected in space. So here, for instance, we have a battery kind of in the center, and the current splits. Some of it goes to a capacitor, some of it goes to a resistor. Current going through the resistor will eventually get back to the battery there. The capacitor looks like it will stop current, but what will happen actually is current will kind of flow and charge will build up on the capacitor, which will push positive charges away from this plate. And at least at the beginning, there will be current that flows this way and then eventually getting back to the battery. So even though a capacitor is in a circuit, it doesn't always block current. To kind of clean up this diagram, we would kind of draw it like this. So the battery is always over to the right, or I'm sorry, to the left. And the voltage difference on the battery is always written as a kind of curly letter E like this. So if the battery gives the charges moving through the circuit a boost of, let's say, 9 volts of potential energy, that means this letter E here stands in for that 9 volts. The resistance of a resistor is R, and capacitors, we'll get to those on Wednesday. So for now, I'll just kind of not talk about that much, other than to say that this circuit here, we have the current splitting from the battery and going to the resistor, the capacitor, and then getting back to the battery. Both of these things show the same logical equivalent. So the battery is there, the resistor is there, the capacitor is over here. So even though we've drawn them in different orders, the diagram still shows the same logical thing happening. Current coming from the battery, splitting through the resistor and then the capacitor, and then coming back together at the negative end of the battery. if you study circuits or you work with circuits a lot or take a class in electronics, learning to draw simplified circuit diagrams is a skill and an art form in itself, because you can build things that are quite complicated and have a lot of different connections. And this is generally a good example of why we use these circuit diagrams, because if you just try to take a picture of some of the stuff you build, you can't really make sense what's going on. Sometimes even if you have the circuit diagram, it's hard enough. But it's we're not going to be doing much of this. There will be a few problems on the next problem set that ask you to you'll be given a picture like this and asked to pick the right diagram here. So that'll be one type of problem you have coming up. You should have like a basic idea of what these symbols mean and how it relates to the actual thing you have in the lab. But by and large, we're not going to be spending too much time on it. But you should be prepared for one or two conceptual problems asking you to convert from picture to circuit schematic. Does that make sense to anyone? If you have any questions, of course, feel free to type them out and stop me at any point. You could also use the raise hand feature in Zoom to get my attention at any time. Okay, so we want to figure out, when we're talking about circuits as we go in thinking about physics problems regarding circuits, our main goal is going to be to figure out, given like a battery and a different number of resistors in a circuit, what's the current? Or if we know the current, how can we find what the resistance is? Or if we know the resistance and the current, what's the voltage from the battery? So there's a few different circuit laws that we're going to use. Most of them we already know. So they're basically kind of rules for circuits. So there's going to be about 5 of them, and I'm going to give you them here, and then we'll kind of talk through some examples of how this works. Okay, just so you guys are aware, a few of you have microphones that seem to be leaking through noise. If you guys could mute them now for a second, just so it doesn't, just check your microphone, thanks. All right, so our first 2 circuit laws are basically things we already know, though they're named after Gustav Kirchhoff again. We've seen these before. One is Kirchhoff's junction law that we learned about Kirchhoff's junction law that we learned about last Friday. This is just saying that current is conserved. So all the current going in has to be equal to all the current coming out. So here, in this case, I1 is equal to I2 plus I3. The second rule for circuit is called Kirchhoff's loop law, which says that if you have different things inside of a circuit and current is moving through all those things, the change in voltage around the whole circuit must be equal to 0. So what that means is that, let's say like this first element here was a battery, and we have current moving through, and the battery is a 9-volt battery that gives all of these gives all the charges moving around in this current some energy. That means that if these other things here are all resistors, that as the current moves through these 3 resistors, it has to eventually lose all this energy it gained from the battery. So if these are all equal resistors, at some point as the current moves through, it has to lose a little bit of voltage here, a little bit of voltage here, a little bit of voltage here, but all of these losses have to add up to 9. So basically what this is saying, Kirchhoff's loop law is essentially just conservation of energy. The energy you gain from a battery must be lost in some way as the current moves through all of the other things in the circuit. Regardless of how it gets back to the battery, once it gets back to the other end of the battery, it has to lose all that energy that you gained. Essentially, it's like the charges have to go uphill as they move through the battery, and then they move downhill as they go through all the other elements. So often the ways you lose energy can vary. If it's a tungsten resistor, the charges have all these collisions and they lose that energy as heat. If it's a light bulb, then the resistor is built to give off energy as light as well. So these voltage gain from a battery are the charges gaining energy. The voltage lost in a resistor or a light bulb is representing all the energy lost to collisions, to heat, to light, etc. So that's rule number 2, which we'll come back to when we come back to our problems. Rule number 3 is Ohm's law, which we talked about on Friday, that current is proportional to, the current through a resistor is proportional to how much the change in potential energy or voltage across the resistor, and inversely proportional to the resistance. So this allows us, this is going to be really important in a lot of circuit problems, because it will allow us to, if we know how much energy we lose over a resistor, and we know the resistance, that will allow us to find an unknown current. So this is kind of like a key, this here is a key rule for a lot of circuit problems. We'll come back to it again and again. The last few things we will need are, often we care about not just the energy we lose in a light bulb or in a resistor, but how much energy we lose per second. We care about the power loss or the power consumption of that device. So as I said before, energy is lost as heat in a resistor. And if you want to figure out how much energy is lost per second for a resistor with current going through it, if you know the voltage change or the energy change across the resistor and the current through it, I'm just going to state that the power lost is going to be the current times the voltage, or times the change in energy. Just kind of, I'm not going to really derive this, but just to kind of justify this for you, the units of power are watts, which is joules per second. And if you take a look at our units for current times voltage, you will see that the units of current are coulombs per second, and voltage is proportional to potential energy. It's the ratio of potential energy to charge, so the units are joules per coulomb. And conveniently enough, the coulombs cancel, and you can see that this quantity, current times change in voltage, is joules per second, so it has units of power. We could also kind of combine this rule here with Ohm's law up here to get 2 other formulas for computing the power being consumed by a element or a device in a circuit. So there's 2 other ways to compute power. So for instance, here we could replace delta V with I times R and get this formula here for power. Current squared times resistance. Or we could get rid of current by replacing it with delta V over R and get a third equation for power, which you guys can see here. If we don't know the current in a resistor, but we know the voltage loss through it and its resistance, we could still compute the power. So these all give you kind of the same thing. And that's the last kind of new formula for today. I know this it's kind of a lot that I'm giving you right now, but I find it's best to just kind of work through a few circuit problems. So for today's class, what I'm going to do, there's going to be one or two problems that I just kind of work through, and then I will give you guys a similar example to work through after you see me work through a problem, just so you can kind of get an idea of what it looks like. Any questions on the theory before I move on? Okay, then let's take a look, and I'm going to do just one kind of the simplest circuit example that you can look at here. This is just going to be one battery connected to one resistor. I'm not going to put numbers in yet, or at least not going to work through the numbers, but let's say the battery here is a 9-volt battery. So we have current moving, the battery is going to separate charge, and when we connect wires to each side of the battery through the resistor, this whole loop is going to allow current to move. Again, we're going to pretend the positive charges are moving. So we're going to assume current moves this way from positive to negative. So I'm going to ask you guys here a question for you guys to answer in the chat. If this battery here is 9 volts, what is the voltage lost or the energy lost over the resistor? So what is delta VR? If we gain 9 volts from the battery, how much do we lose over this resistor? Okay, so Brody says 9 volts. And I'm going to agree. In reality, it's not perfectly 9 volts because no wire is perfectly conductive. So in actuality, you lose a little bit of voltage across all these wires. But as far as our problems are concerned, we're going to make the simplifying assumption that all wires like this are perfectly conductive. There's no resistance whatsoever. So therefore, the voltage lost over the resistor is minus 9 volts. So we're going to ignore the fact that even these copper wires or whatever have a little bit of resistance. The only things that have resistance in circuits are things that look like this. Okay, so voltage source here, this curly letter E is just a positive increase in potential energy or a voltage increase. Oh, this was supposed to be a kind of an animation, but it doesn't seem to be working right now. It was supposed to have all these charges kind of moving. So it kind of gives you the hill example. So the battery is kind of like an escalator or pump that gives the charges, moves them uphill, and then they roll downhill. And the resistor is kind of like this fan wheel. It takes their energy and starts rotating. Right. Sad that didn't work. Oh well. It was working before, but it must be something with the sharing screen in Zoom that caused it to stop working. So here, our main equation for this circuit is, this is our Kirchhoff's loop law, or our conservation of energy, that in magnitude, these two have to be equal. Of course, there's a minus sign there. But let's say we want to find this current that's moving around the circuit. If we wanted to find numerically what that current is, we could use Ohm's law along with these numbers here. So let's say that this resistor is, we'll make the numbers fairly easy to do the math right now. So let's say this is a 9 ohm resistor. if we wanted to find the current through the resistor, we could take the magnitude of this voltage, the voltage across the resistor, and the resistance, and divide them. Since these two are equal, we're going to have 9 volts divided by 9 ohms, meaning our current will be 1 amp. And it would be moving from the positive side of the resistor to the negative side. Of course, what's actually moving here are the electrons, and they're moving in reverse. But we're not going to, as we talked about that on Friday, we're going to assume the positive charges move. So that's kind of the simplest circuit example you can do. However, you could have more complicated circuit problems. For instance, circuits where you have more than one resistor. And depending on how the resistors are arranged, the problem can become more or less complicated. So for instance here, we have 2 resistors connected to a battery. The total current coming from the battery has to go through both resistors. So in this case, the voltage across one resistor plus the voltage across the second resistor, if we use Kirchhoff's loop law, or conservation of energy, these two added together have to be equal to the voltage gain from the battery. So we could kind of think about these things. If you want 2 resistors in this configuration where the current goes through one and then all through the other, we call that resistors in series. And we say that they have an equivalent resistance, so they can be thought of as just one big resistor with resistance R1 plus R2. And we call that the equivalent resistor or equivalent resistance. This works for however many resistors you have in series as well. Whether you have 3 or 4 in a line like this, you can always take them and replace them with one resistor with a resistance equal to their sum. And that kind of allows you to kind of simplify the math a bit when you're solving for the current in circuits, so on and so forth. Colleen, that's a good question. So would the power loss be broken up equally among the resistors, or the energy loss? So I think what you're asking here is would delta V1 and delta V2 be equal? And the answer is it depends. So if the 2 resistors if R1 and R2 have the same resistance, then the charges will lose the same amount of energy across both resistors. However, if one has a bigger resistance than the other, more energy will be lost over the bigger resistance. The total energy loss still needs to be equal to the total energy gained from the battery. But more energy will always be lost over the bigger resistor. Does that make sense? That's a very good question. Okay, good. So, oh man, there it's working now. Okay, so you guys can see that. Okay, that makes me happy. All right, okay, moving forward. So this is one type of situation you could have in circuits with resistors. However, there's another type. It's when the current splits and goes part through one resistor, part through the other. That's what we call resistors in parallel. And that's something that looks like this. And here, the rule we can still kind of take these 2 resistors and replace them with an equivalent resistor. However, the rule is different. So the equivalent resistance, the resistors don't just add together like they did when the resistors were in series. It's the inverses of the resistances that add. And this is all because the current splits. So I'm going to explain why this is in a second, but if you could copy down both of these equations, we'll use them in a few more examples in a second. So the reason why we have this different rule is because when we connect resistors like this, where we cause the current to split between one resistor and another, overall, we end up getting more current through the circuit than we would have otherwise if we just had one of the resistors or the other. And I call this in circuits the toll booth effect. So you can kind of imagine like that you're stuck at a toll booth. Maybe it's at the Bay Bridge or something in the summer, and there's a big backup, and they only have one lane open. However, you're like waiting there for like 30 minutes, an hour, getting really frustrated because the traffic's moving so slowly. And then partway through, they decide to open up a new lane. That new lane is still slowing down all the traffic, but the fact that it's open causes traffic as a whole to move a little bit quicker than it would with just one lane open. So that's kind of why, even though when you're adding a new resistor here to the circuit, it still ends up letting more current through because it's like opening up a new lane in the toll booth. So it still has a resistance, but the net effect is to allow more charge to move. So when you add a resistor in parallel to this, it's almost like you're effectively lowering the total overall resistance. And that's why you have this new rule where the inverses of the resistors add to give you the new equivalent resistance. It's still the higher resistance path is going to allow less current or less charge to move through than the lower resistance path, but the net effect is still to let more current through. So because of this, this is why we have this different rule for resistors, what we say in parallel. The inverses of the resistances add, and the equivalent resistor that we would replace them with is overall lower resistance than either R1 or R2 or R3 if we add a third one. And that's why we have this different rule. So let me give you an example of how we would use these rules in circuits. This is going to be a problem that I kind of worked through, and then I'll give you guys one to work through that's similar to this afterwards. So here, this is like an example of a fairly kind of common circuit problem. So here, what we're told is that we have a 9-volt battery connected to 3 resistors in series. We know that the current, we can measure the current coming from the battery with a current meter, which I would have had you guys do in lab, but unfortunately we won't be able to. But we measure that current to be 1 amp, so 1 coulomb per second. And we want to use this information to get the value of the unknown resistance. So what is R here? So how can we do this? There's several ways we can do this. One, we can, you might think we can use Ohm's law and find delta V on each resistor separately. So we have the current, we have the resistance, we could solve for delta V1 here, delta V2, and then use the loop law to get the unknown voltage here, and then Ohm's law again to get the unknown resistance. And that would work. It's a whole lot of steps though. So we can use the equivalent resistor rule to kind of get to the answer more quickly. So for instance here, we can take all of these resistors and replace them with an equivalent resistance. That would effectively, so we could take this 9-volt battery, and instead of having these 3 resistors here, take our battery and connect them to just one resistor with the equivalent resistance. The whole point of that equivalent resistance is that it doesn't change anything in the circuit. So we still get 1 amp of current coming through for a 9-volt battery. And we could use Ohm's law to now find the equivalent resistance. So we have a 9-volt difference, 9-volt loss on this equivalent resistor, and a 1 amp current. That means the equivalent resistor must be 9 ohms. But we know, since all 3 of these are in series, that these 3 resistances must add up to the equivalent resistor. That gives us enough information to solve for this unknown resistance R3. So R1 is 3 ohms, R2 is 2.5 ohms, R3 is unknown, but if we add them up, we get 9 ohms total. Oops, sorry about that. Looks like I drew over this equation. Let me just reset the slide. So from here, we could solve for R3, and we realize it has to be 3.5 ohms. So by taking, essentially this equivalent resistor rule allows us to simplify this circuit to solve for some unknown quantities. And same thing for the parallel equivalent resistor rule. So what I'm going to try to do here is give you guys a similar problem. So here, we know the 2 resistors. Let's find the current from this information. If you have any questions, then let me know. If not, then I'll be quiet and let you guys work for a bit. So from here, the strategy is find the equivalent resistor, then use Ohm's law to get the current. And then when you got the current, text your answer A, B, C, D, or E in the chat. All right, a lot of answers right now in the chat, all D. So you guys are good there. Looks like you got that. So here you replace the 2 resistors with their equivalent, which is 18 ohms. Use Ohm's law to get the current. So it seems like you guys got that quickly. Let's try one with parallel resistors then. So here we have, again, a 12-volt battery. And we want to know the total current coming from the battery. So here we have a total current I, and then it splits. We unfortunately don't know I1, I2, or I3. We could use Ohm's law and figure out I1 or I2 or I3. But quicker solution is to use equivalent resistors. Take these 3 and replace them with their equivalent, and then use that to find I. So here you have to use the parallel equivalent rule. So you add the inverses, and you should see the equivalent resistor has a, it's lower than any of these 3, because we're allowing, by adding the 3 paths, we allow more current through. So try this, try to find the current I here, and then when you have a number for the current this time, text it in the chat, and I'll wait for you guys to give me some answers. If you have any questions, feel free to ask too. All right, so it looks like as you guys work, I'm seeing kind of 2 different answers here. two 18 amps and about 2/3 of an amp. So we'll see what it is in a second, but 218 seems quite big. Remember, 1 to 10 amps is a household current range. So that seems fairly high for a 12-volt battery. So I go and check your algebra again. But keep working, guys, and as more people get an answer, text it, and we'll see where people are, where people's answers are falling. I'll kind of give you guys the first step here, though, is we want to find the equivalent resistor and then replace these three with that equivalent. And then use that to find the total current. Okay, I think usually what happens here, if you're getting the 218.2 amps, often you may have just solved for 1 over R equivalent instead of R equivalent. So remember, 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over R equivalent. And then you have to invert the whole thing again to get the equivalent resistor. So often that's a step that's forgotten here. All right. Cool. It seems the people got 218 corrected their answers, now getting 2/3. Can I ask you guys just to, was this the mistake? Forgetting to do 1 over R equivalent? Okay, yeah, common, that happens a lot. Don't, that's like the main common mistake with these parallel resistors. Total current then is the battery voltage divided by the total equivalent resistance and gives you 0.66 amps. You can then, with that information, if you wanted to find I1, I2, and I3, you can then work, there are ways to find that too. For instance here, though we're not going to do it in this problem, we could use the loop law to do so. So the battery gives us 12 volts of potential energy. These 3 resistors, you can think of them like 3 different ways to go back down the hill. So for instance here, that means that if we gain 12 volts from the battery, the current that goes this way through the first resistor has to lose 12 volts across that resistor. There's no way around it. The current that goes through the second resistor also has to lose 12 volts. No way around it, because it's like a separate path down the hill. Similar for the third resistor. So if you did want to find the individual currents here through each resistor, you can do that using Ohm's law on the individual resistors, and you should see that if you found I1, I2, and I3 that way, and you add them all up, you should see that they add up to 0.66 amps, or 2/3 of an amp. I'll leave that to you guys as extra practice. I know I'm hitting the end of my time here, so it's 10:20, but I do have one more problem, example problem for you guys to work through that will help for the homework this week. If you have to leave, I understand, it'll be posted this afternoon. But if you want to hang out and do one more problem, I think it'll help for the homework this week. Okay, any other questions on this one before we do the last one? Okay. So I'll leave, this is the one I want to do. Sometimes you get situations where you have complicated combinations of things in a circuit that aren't really totally parallel or totally series. So for instance, that's an example here where we have a battery and then two resistors in parallel, but then the current comes together again and all goes through this third resistor. How do we handle a situation like this? And basically the idea is that you have to kind of take the circuit, you have to work with the circuit in parts and replace different parts of the circuit with their equivalent resistance. So for instance here, we could look at this parallel segment, these like two resistors in parallel, and replace just those with their equivalent resistance. And then draw the new circuit and then find the equivalent resistance like that. And we end up working in steps until we get down to just one equivalent resistor. So we have to kind of look for pairs of series or parallel resistors and replace those pairs with an equivalent and then redraw the circuit. So you kind of have to work in steps here. So for instance here, these two parallel resistors, that's what I kind of see first. I could replace those with an equivalent. And if I work that out, 1 over 10 plus 1 over 10 gives me 1 over 5. Inverting that, it gives me 5 ohms. So I can replace these two parallel 10 ohm resistors with one 5 ohm resistor. And now I have two resistors in series. So I can do this whole step again to now replace these two with an equivalent resistor of 5 plus 5 is 10 ohms. So notice the step here. We do this equivalent resistor process twice. Just going back, we start with 3 resistors arranged like so, replace those 2 with their equivalent, and then out of now the remaining, we can replace those 2 with an equivalent resistor of 10. If we go through this process, the idea being is that this equivalent resistor of 10 ohms will cause the same current to flow from the battery as that original situation with the 3 resistors. So we can then kind of find the total current coming from the battery using that equivalent resistor. So that total current coming from the battery is 1 amp, 10 volts divided by 10 ohms. So we can now use this information in the original circuit. So we go back to that original circuit, and we know that there's now 1 amp of current coming from the battery. That must split between these two resistors and come back together here in the 5 ohm resistor. So if we wanted to find the voltage lost on this 5 ohm resistor, we can now do that using Ohm's law. So we now know that there's 1 amp, there must be 1 amp of current going through that 5 ohm resistor. That means we must lose 5 volts across that 5 ohm resistor, The last step is if we wanted, the only other remaining unknown information in the circuit is the voltage loss across these two 10 ohm resistors. Well, we could solve for that information just by using the loop law, or conservation of energy. If we gain 10 volts across the battery, from the battery, then we lose 5 volts of potential energy here on this resistor, the charges moving have to lose the other 5 on either of those 10 ohm resistors. So by the loop law, we know that the voltage lost on both of those other resistors has to be the other 5 volts. There's no other place to lose that energy. So using this process of equivalent resistors twice and then Ohm's law on various parts of the circuit, you can take this information and then basically solve for any amount of unknown information in the circuit, regardless of what voltage you're looking for, or what current. You can solve for all of that information using these equivalent resistor rules, conservation of energy, and Ohm's law. So if you wanted to find the individual, the currents going through each of these 10 ohm resistors, you can now do that using Ohm's law. I'll leave that to you guys. Or you could use some logical reasoning to figure out kind of how the current must split. But I'll leave that as a extra practice for you guys. So you'll see in your in the homework this week kind of 5 problems that all kind of are modeled on similar to these. So if you can, I would consider going and trying them now if you want. That's the last problem I have to do with you guys today. So I'll post the slides soon. If you have any questions about this homework or the next one, feel free to let me know. And if anyone wants to stay, have extra questions, or you want to do this third example problem here, I'm happy to talk through that, but I'll wait to see if anyone stays.